Thank you very much for your kind introduction. Thank you, Anatoly. Unfortunately, my Russian is not that good, but always your talks and lectures are highly stimulating and highly intellectually challenging. So it's fantastic. Good to see you again. Good to see you all again. I will start my talk shortly just to warn the guests who had attended the Saturday's meeting. You may find some of my material repetition, so I hope it doesn't bore you. And I hope you enjoy the talk as much as possible. I will try to now share my screen. Do you have my screen now?
Yes, we do.
Excellent. Okay, today's talk is about the digital transformation of industrial systems, the roadmap to Industry 4.0. And I will start with the systems philosophy and systems engineering, the modus operandi of what we consider as systems engineering approach to achieving Industry 4.0. And then I will go into some details of some industrial examples, some more detail on event-based modeling, and then hopefully questions and answers. So, the evolution of systems thinking. If we look at the how systems approach has evolved throughout the history, if we go back to Aristotle and later on Newton, who basically moved from the philosophy into the science of systems, there was a mechanist approach where total of the system was defined by some of its parts. Basically, these systems were designed and developed or interpreted as fixed systems, normally repetitive, algorithmic, with a fixed logic. So basically, for example, if you have a bicycle, the totality of the system is the definition of every single part of it. If you remove one of those parts from the system basically loses its being. So for example, if you remove the saddle from a bicycle, then it's not anymore a bicycle. It's just a combination of entities connected to one another. The major challenge to mechanists came from organists. Basically, the challenge came in the late 19th century, mid-19th century to late 19th century and early 20th century by people who looked at systems as not only just a simple interaction between fixed components. These systems were more in adaptation with their environment. They had sensing capabilities and had the ability to evolve as their surroundings moved towards changes. And again, in the early to mid 20th century, the ideas of adaptive systems, which were well defined in mathematics and in control systems, they also have the challenge of, okay, a lot of adaptive systems seem to lack the intelligence to look forward ahead of time and make changes to themselves predictively. We moved into viable and sustainable systems. These systems were denoted by smart intelligence. They were intelligence. They have the agility to further not only adapt to the system, but they were active learners. These active learners used their sensing capabilities and technologies to understand their surrounding much better. So they were active learners. They were aggressive predictors, and they had the ability to master complexity. They not only adapt to their environment, but with a good understanding of their environment, they also influence the environment towards viability and sustainability. So they expand and extract as their environment changes. When we superimpose that sort of thinking, we go back how the evolution of industrial systems also sort of adapted itself to this evolution. If we go back to industry, the first generation of industrial systems emerging from industrial revolution in the mid-19th century, we had job shop, highly skilled, make-to-order systems where engineering disciplines sort of controlled and led these systems. Classical engineering disciplines were the major incubators and the guardians and custodians of these sort of systems. In the early to mid 20th century, with Henry Ford as one of the pioneers, the idea of mass production came to the fore. In these type of systems, standardization became a target. Machine tools evolved and improved to create automation and more specialist activities. Serialization was a major achievement there. This way, to reduce the cost of production and create products and services that required lower skills with more attention to tools and equipment. Here, the management science and operations research took the initiative and developed techniques on optimization and improvement of processes. As the 1950s and 60s, we got the advent of automation and robotics, where control engineers and automation engineers, using the combination of mechanical engineering and electronics and electrical engineering, combined their capabilities and took a lot of good things from the previous accumulation of science and technology to create robots and automated systems. However, the robots and automation was still repetitive, algorithmic, and lacked high intelligence. So with the turn of century and when we came to the 21st century, the new ideas came in: active learning, big data, the capabilities of acquiring larger sets of data, better information, and collection and storage and advancements in computing technologies enabled us to be more aggressive predictors, govern complexity. So not only our artifacts became more complex due to their complex material, but also functions and operational achievements with networking, with combination of smaller systems and components. We see new products and solutions denoted by cyber physical systems. These systems have a capability to continuously monitor the behavior internally and externally, and have high levels of optimization, so improving themselves better and better. And finally, we reach the stage of sustainability, zero waste manufacturing. One of the avant-gardes of industrial systems is manufacturing. Most of our wealth is generated from added value in manufacturing systems. Here, with the embedding of advanced ICT capabilities, information and communication technology, machine learning, and artificial intelligence, we are seeing smarter machines, smarter processes, and smarter autonomous and autonomy of systems. So, what is the fourth generation industry? The fourth generation of industry, especially a catalyst for manufacturing and the associated service sectors, is a web of interdependencies of a range of technologies and concepts. It includes Internet of Things, the connection and interrelationship between the components of systems. It has a much more complex logic. Big data. Big data means not only the volume, but the breadth. So we have a wider range of information. It's like when we think about how we're seeing now, if before we saw with our naked eyes, later on by binoculars, now big data is giving us a telescopic or microscopic view, a larger and wider range of vision. Cloud computing is another enabler. So basically, large capabilities of data storage, data analytics, and interfacing with different sources. These systems are highly, now that it is becoming interrelated, cybersecurity has become a major issue in these areas. So how do we retain and maintain the health of our systems, our interconnected systems, through ensuring that no malfunctions occur due to intended or unintended mistakes and faults. Robotics has moved to a new level, robotics and automation. We are going towards a digital society, a society that intelligence is being generated through a strong transformation of physical or interpretation of physical systems into their digital clones or digital twins, as we call it now. And now, although the word artificial intelligence has been around for nearly half a century, now it is becoming a reality. How we are using our computational capabilities to generate new intelligence, new knowledge that is now going to be helping both man-made systems and even natural systems more attuned to the way that we think and the way we control systems. So we are creating the web of interdependencies. And this web of interdependencies requires the building of an information-rich environment in which the dynamics of the real world, demand and supply, are integrated, heavily monitored, and optimized. And more importantly, these enabling technologies will allow for real-time and predictive adjustments of operations by utilizing the evolving data analytics methods. That's where your aggressive prediction comes into the fore. So if we look at the value creation of cycle of Industry 4.0, we see a wheel that continuously revolves. The real world of manufacturing processes or systems processes, business systems processes, and the physical value, the physical entity of information. Our systems are generating data through sensors and actuators. Sorry. This data that is generated is now being shared amongst the internal components of the system, but also in its immediate vicinity and beyond. This continuous condition awareness, situation awareness, is enabling us to be able to use our scientific methods to analyze this data and better understand the state of systems. Through this better understanding of state, we generate the knowledge, and then we say, oh, we can improve it. We can do better things. So optimization techniques are taking role in this look forward mechanism and continuously adjusting and upgrading our processes. We are now in the verge of claiming that we are going to build processes and systems that do not anymore create defective products. So no waste of material. We are on the verge of claiming that our artifacts will never fail during their operations. Zero breakdown. We are on the verge of saying or creating interlinked and interrelated systems that correct each other's behaviors. Going back to the systems philosophy, we are creating an infinite loop of optimization and adjustment. When we have the physical system, which is highly now embedded with sensors and actuators that continuously inform us of their state, we have the capability of taking those data points and analyzing that information in real time. Through that, in the process of digitalization, we create models, mathematical and symbolic representations of our physical systems that are highly accurate with high fidelity. We have the techniques and methodologies to test and ensure that what we have modeled and digitalized highly conforms to our physical world. And where there are inaccuracies, we will go back and improve our data acquisition methods, our data analytic methods, and our mathematical models. In this process, we create a digital twin. A digital twin that enables us to visualize the real system, share this knowledge with all the people that have the expertise and insight to suggest new ideas. So these sustainable systems are highly innovative and inventive. And now, because we have a digital representation, it gives us the confidence to deploy and employ optimization tools or ideas, test it without interrupting the physical system. And once we have the high assurance that the changes, the upgrades are verified and implementable, we can now go back and change and upgrade our physical systems. And this is now being deployed in continuous processes, in discrete processes, and now even biological processes. We not only improve processes, the method of evolving material, raw material, but also influencing the design. So what is the modus operandi? How do we make this happen? What are the tools? In our own system engineering research group in Brunel University, we deployed two approaches. One is the classical and traditional method. What do we mean by that? Is that we collect the data from the plant. We analyze the data through feature extractions, signal processing, filtering, and validation. And take this known knowledge and build system state models using mathematical tools and techniques. Transfer functions that represent the system. These are through physical models. So these are phenomenological models or inferential models through the observations and statistical means. Regress and build inferential models, or where both techniques do not provide us with representative models, we use heuristic methods. This is where the white models, gray models, and black box models come to the fore. However, in some occasions, we have realized that the traditional and classical methods of learning and deep learning and understanding of systems and translation into transfer functions do not fully lend themselves to practical applications. There are processes that we need faster realization of corrective actions, actuations. So how can we reduce this lead time? Normally, these techniques, the traditional techniques, they're data hungry. There are many occasions that we do not have that much data. It doesn't exist. So we suggested the event tracking system, an unbiased, unaware data mining technique and data and feature extraction technique. In this method, we are suggesting a digital monitoring and control mechanism. We use a simple philosophical method of the relationship between parameters. If something changes and another system within the observed world change together, or in a sequence of one another, in a known sequence of one another, then there's a logical relationship between them. If this doesn't change and this doesn't change, then there's a logical relationship between them. If this doesn't change and this changes, there is no relationship between them. If this changes and this doesn't change, there's no relationship between them. And if this coincidence is repeated, then our understanding is that there is a correlation between them. So in this observation, during a short period of time, we can capture the sensitivity of the output parameter to a series of input parameters. In this small example, we have the blue sensor, the red sensor, and the green sensor, and its impact on the output, or its coincidence of changes. And as you see, in time, once the system reaches its stability pattern, steady state, we realize in this example that the red sensor and the green sensor are highly related to the output parameter, but the blue sensor has no relationship to it. From this many-to-one relationship, we extract the weights or the sensitivity values of system input parameters to output. In another action of clustering, we now look at many-to-one relationships, series of outputs to series of inputs. And as the system goes through its life cycle, like a clip in a movie, we create the relationship between system input parameters and output parameters, and each of these boxes or each of these matrices provides us with one snapshot of the system state. So each of these are system state with their own parametric values. Now, in order to validate and verify whether these states are transient states or one-off states or real states, we look at them, whether they are repeated continuously within the system life cycle. Through this pattern, we extract the genealogy of system state. So each state can now be represented by a visual or a physical or a digital format. Through this, we build the DNA of process. The causal relationship and causal link between the input parameters and the output parameters, the way the system manifests itself. So, from this method, we generate a lookup solution. And through this lookup solution, by returning back to the key values of the system, we identify the optimal performance based on the objective functions and the suboptimal performance. And when the system goes towards suboptimal performances, we can alert the autonomous system or the operator of what needs to be done, how you have to return the parameters of the system back to the actual system, the better performing systems, and its impact on the outputs. Through a simulator, we test it, and if it works, we go back with the actuation and change the parameters to those settings. It's like when you are tuning your violin. Now, the beauty of this approach is in its quickness, because it's all digital. However, we do not only rely on this, but we have created a link between the traditional models, mathematical models, and the digital models. So this digital model, which now has no bias, so in other words, it has an infinite set of input parameters, IoT. Traditionally, we had fixed inputs and fixed outputs, because that was the way we were building this. Through this, we can now adjust our mathematical models. The correlation changes between system parameters in real time, and also the introduction of new variables as the system evolves, either towards decay or towards upgrades and updates. So these two correct each other. This solution provides us with the boundaries and continuum. This is digital discretization, and this is continuum and continuity, continuous systems. Through these two, we improve each other for a more accurate and more responsive system. So high fidelity. So current systems relies heavily on our knowing the current way of us doing work. And as a traditional control engineer, I was told that you know your system input parameters, You know what you want to take out of it. You know your output. Ensure that these things work and build a model towards it. In event modeling, I have no bias. I open my system to potentially an infinite number of input parameters. The observed world or the observable world. So everything in the world has an impact on my system output unless proven otherwise. So that's how the event model works. So in this model, we have our data acquisition layers, which consists of individual components, which continuously tell us about their state. This could be a ball bearing in a revolving machine that with listening to it, I know whether it is in good condition or not, for example. It is a chemical mixture that through its change of, through the chemical interactions, it is generating heat or a type of gas in a vessel or changing color. It could be a combination of components that are represented as a device. So a combination of things. So it could be a hydraulic system that is given its status. It could be a network of components or devices. So the first three gives us the internal dynamics of the system and representation. And then you have your environmental information. So I have a car that I'm driving. It is the same car. It's the same BMW that was manufactured in Germany, for example, but it goes to worldwide users. Each use their cars in their own way. They service the cars their own way. They drive in a specific condition. The driver is different. The way I drive is different from the way you drive. So that information also impacts the behavior and the evolution of your system. Through that combination, I build a highly customized digital twin or situation awareness. And based on the real world, I will build a customized optimizer, performance optimizer. So I will build a, let's say, a zero breakdown machine that works, or a generator or power generator that works in a Malaysian humid, hot environment, same machine. And one that works in North Pole or South Pole with its own remaining useful life calculator. Data decomposition and superimposition. So, what are the challenges here? If we consider that the whole process of digital transformation consists of input data validation and verification, feature extraction and sensitivity analysis, systems modeling and simulation, and control optimization. What questions do I have to answer? What are the challenges? How good are the data that I am collecting? Have I put the right observatory technologies in? So the art and science of sensor networks. How do I find a good technique and method to make sense of that data? And what techniques do I have to use to visualize and interpret that data? And once I have high confidence in the accuracy of my interpretation, what actions do I have to take to retain and maintain the longevity and sustainability of that system? So I go through some of the examples that we have experienced, or I have experienced in my own career, and the projects and the challenges that I have been given in these years. The first thing is on sensor and input data validation. One of the most important factors in this transformation or digitalization process is to ensure that the data that I am collecting from my physical system is reliable and good. Within the new environment that we're working, everybody wants cheaper solutions, lower cost techniques. So one of the problems with cheaper solutions and lower cost techniques is dealing with the intermittency and connection failure of sensors, or cheap, low-cost sensors that may at times provide you with wrong information. A lot of these applications is in wireless control area networks, because you're using low-cost sensors, and mainly you are using, in order to reduce the cost of wiring, or there's limitations in using wires, you have wireless sensors. Traditionally, Kalman filters are used for error estimation. So we have iterative Kalman filters, particle Kalman filters, or now more useful in communication technologies, Tobit Kalman filters for dealing with estimated errors. These are to assess and evaluate censored observations, lost information. Recently, we just nearly now in the final stages of publishing a paper in IEEE Transactions of Signal Processing on a method called protocol-based Tobit Kalman filters. We use a covariance state estimation to compensate and improve our knowledge of what sort of data we have lost and find methods of compensating for that. We're hoping with this method, we can have a more representative augmentation, induction, and integration of good quality data and compensating for the lost data. Where do we use this? Interestingly, is in low-cost precision farming. We have a project for maintaining and retaining, preserving water and irrigation systems in water-scarce islands of Mediterranean. In another example, we have realized that a single method of looking at something is not sufficient to provide us with sufficient knowledge to take action. So we have offered sensor fusion. In a recent project, we were tasked to assess and evaluate the quality and the security of electronic circuits and boards. Traditional methods use optical image processing. It still is, even in factories, there are people sitting and looking at those boards to ensure their quality and whether there's no tampering in it, et cetera, et cetera. We realize that these image techniques, surface imaging, is not sufficient to finally detect the fine discrepancies. So like Superman, we created penetrating technology as well. We introduced penetrating technologies as well. So combination of X-ray and optical and surface now gives us a better representation of the systems. In this way, we can now detect anomalies much more accurately and in much more depth. So we expanded big data, we expanded the kind of seeing things, and from that, we have improved the quality of our data analytics and interpretations. In another example, at times, there may be solutions for acquiring information from your physical system. But they are very expensive. And one of the examples that we have is in order to reduce the greenhouse gas emissions in water industry, in water treatment industry, and the energy consumption. We want to measure the amount of nitrogen oxide emissions. Nitrogen oxide is 100 times more potent in greenhouse gas emission and global warming than carbon. So one of the ways to mitigate and control climate change is to reduce nitrogen oxide or to control nitrogen oxide emissions. Simply to put a nitrogen oxide sensor, we have a gas analyzer into a water treatment plant, one system, will cost you over £150,000. This is forbidding for many water companies and utilities. So in this case, we are introducing self-sensing. So indirect calculation of nitrogen oxide emissions using other observations, other low-cost sensing of the system state. To do this, we have introduced these NO2 sensors in some targeted plants, and we are finding the correlation and relationship between other systems KPIs and parameters against NO2. And through this and validation verification, because they're in different settings, we are trying to now find a good estimator of nitrogen oxide. So in future, instead of telling and going to every single water plant and asking them to install very expensive sensors, we will say that if you put these cheaper sensors, cheaper data acquisition technologies, indirectly, we will measure your nitrogen oxide emissions. Also, this nitrogen oxide, this method of intelligent system monitoring is helping to reduce energy consumption in water treatment plants. 6% of EU's energy consumption, the total energy consumption in EU, is for water treatment. So you can imagine the billions of dollars that has been spent, or euros that has been spent on supplying energy to treat water. So any improvement in process and reduction in energy consumption is highly desirable. And this is one of the targets of the projects that we do. And as you see, the proliferation of sensor technology and adoption in industries, various industries around the world. So there is a lot of investment in smartification, processes, machines, and equipment. The next challenge is, now that we are confident about the input data, what sort of techniques and mechanisms can we use to translate that information to models, representation of the system? Due to the advent of data-driven modeling, moving towards data-driven modeling, deep learning and neural networks and learning mechanism, machine learning, has come to the fore. I remember, Anatoly, a few years ago when we discussed, and I didn't know anything about machine learning, you told me, Ali, go towards machine learning, and thank you very much for that advice, because it helped me to argue the cases of modeling and data acquisition much better. It had expanded the audience. I owe this to you. So, in this quest for better understanding and better modeling, we realize that in many occasions, classical techniques of neural networks and deep learning are not helpful in our systems, because these type of learning mechanisms are heavily reliant on large volume of known data. If I want to detect defects in wafers, microelectronic wafers and silicon wafers, I need to have a lot of samples, images of a lot of samples that could tell me and give me a good confidence that I can teach or I can train my neural networks to detect. But we don't have that many information. It happens once or twice in the whole process. So we have come up with alternative methods. One of the techniques we have used in our detection of defects or anomalies or abnormalities in printed circuits is something that we have developed called entropy gray imaging process. We compared this with a histogram by oriented gradients and SVMs, support vector machines, which is one of the most prominent technique in image analysis. And in one of our projects, which the speed of detection is highly important because it's a fast-moving system, high variety, fast-moving system. Our EGI, in compared with Hawk's SVM, although we lose the accuracy by 0.8%, the speed of detection in EGI compared to Hawk SVM is 40 times faster. To analyze a laptop board, for example, it takes Hawk SVM nearly 2 minutes to analyze the system, the image. EGI takes around 3 seconds. So you can imagine if you are running an airport security system, how much a fast analytics would enable you to process the people in the system. I have another project with Bosch on autonomous vehicles, situation awareness and safety. We're using event modeling and event tracking to increase the size of data input acquisition, but at the same time, increase the responsiveness of the safety system. In another example, in avionics, with a BAE aircraft with terabytes of data on various maneuverability of the system and condition awareness as the system goes into destabilized situation. We use our event-based modeling against entropy-based analysis, because entropy-based analysis is one of the closest to real-time systems, or the most. In our example of maneuvering correction and analysis, the entropy-based system took 300 milliseconds to assess the situation, whilst our event-based system took only 5 milliseconds to identify the sensitivity. You can see 1/60th of the speed. These are more on smartification of cyber-physical systems, but also we use our hybrid techniques, combination of shallow learning and deep learning and something in between, to deal with more complex, larger manufacturing systems. Here, I give you an example of a factory. In a project called Z Factor, a European project, our objective was to generate or create production systems that generate zero defect products. And our target was electronics and microelectronics companies, hard metal and composite material manufacturing processes, and machine tool manufacturing, tooltip manufacturers. So of course, if you only concentrate on quality, you can create a system that generates no fault, no defect, but you have to take hundreds of hours of manufacturing one component and one product to ensure that it's 100% good. You don't have that luxury. You have other factors in production system that you need to observe and create a balance. So it's an multi-objective function. In addition to high quality, you need to ensure productivity. So you have to retain the production flow. You have to ensure that you cap your energy consumption. We were also asked to take the environmental impact into consideration as well. So reduce carbon emission. We were also asked to ensure that the production system is properly fed and properly supplied to avoid any stoppages. So it's a balancing act. In this process, for quality control, we needed to upgrade some of the machines to get a better understanding of inline quality and the condition of the machines. Because healthy products can only be created with healthy machineries and equipment. So we upgraded the machines to provide good information. We brought the intelligence that was with the experts of the system. All right. And we created a big data collider. Multiple information from multiple sources, internal and external. And through that, we created transfer functions for measuring accurately the quality, productivity, energy consumption, environmental, and inventory management. Through that, we have the key performance indicators of the system that are presented in a numerical value. So hundreds of data points or thousands of data points translated into 5 key performance indicators represented in singular metrics. All these metrics translated into cost function or quality loss function. And then we designed and developed a production planner called the green scheduler. An optimal system for zero defect generates an optimal schedule that needs to go and upgrade and adjust the system's parameters. We were sure, because there are a lot of existing schedulers around the world, mathematically beautifully designed. But in my own experience in the last 20 years, whenever I wanted to try a classical or a known scheduler into the system, they never worked. They came with optimal solutions, mathematically verifiable, but practically they were unimplementable. So in order to avoid this, we use the digital twin of the process through the discrete event simulation. So we input the scheduler on a process simulator to ensure that the solution is verifiable and operationally safe. Once we approve this, then it will go to your system. This system is now fully automated and autonomous. And this is going to now be implemented in a number of large international companies as a proper Industry 4.0 solution. Some of the interesting things that we have found as we integrate the cost function, you can see for OEE is this translation of OEE into a universal cost function. So we are translating all these into a common denominator, which is monetary value. As you see, different production scenarios provides you with optimal solutions. So based on different production plans, you will get which setting of the machines provides you with optimal cost function. So you will always retain and maintain. You put the settings where you get the optimal production plan. I think I have another 10 minutes, correct?
You have as much time as you want.
Oh, you're very kind. Okay. I know we'll normally have a Castro-esque mechanism. I can talk for 4 hours for you. So thank you very much. So I will continue with another few minutes if I'm hoping that I'm not boring you. And another example, we are generating, this is another European project called Zero Breakdown. It is a very interesting concept. The idea here is to develop machines and processes that never suddenly break down during the production system. I'll give you an example just to give everybody a view. You know that when you buy a car nowadays, they tell you, okay, this is your planned maintenance. If you go and service the car after 10,000 kilometers or whatever, then you will be guaranteed that your car will never suddenly break down. And normally when you have a planned maintenance, you build your life around that planned maintenance, because you know on the day of so-and-so, you're going to take your car to the garage. So you make preparations to minimize the disruption to your life. So either you hire a car, you prepare yourself, your family for all these things. So you're prepared. So it has minimum disruption or cost to your life. But what happens if suddenly your car, without your notice, suddenly breaks down in the middle of the road or motorway or highway? It really messes up and disrupts your life. This is exactly the same thing in production systems. I can tell you, one of our partners in this project is a company that supplies packaging technology to big companies, pharmaceutical, food industry, etc. For example, Coca-Cola, Pfizer, etc., etc. And these are fast-moving, high-volume production systems. So you need to make, for example, a plastic cap that goes on top of the bottle for 200 caps per minute. A sudden breakdown of these type of machines in a typical beverage company or a pharmaceutical company will cost $5 million an hour. It was very funny. The factory that makes these machines, I remember the managing director, when I went to explain my idea about this project and convince him to join the production, join this consortium, he gave me only 10 minutes to talk to him, you can imagine. He said, if a bomb explodes in the factory, is better than my machine breaks down in the factory. So the idea here is to ensure that doesn't matter where your machines, when you make these machines, you make them in one factory, you try to reduce any variations, so all of them are standard, all of them look the same, work the same, are tested in the same criteria, et cetera, and goes to your end user, your customer. However, your customer, depending on where this factory is, will treat the machine in a different way. As I told you, the way I drive my car is different than the way you drive your car. The way I service my car is different for the way you use. The raw material, the type of material that I put in the system, the type of plastic I put in the system is different from the one that maybe is done in South Africa, from America or Russia or Malaysia or China. So you have a combination of reasons that will make the remaining useful life of your equipment very different. Our job in this project was to find the exact remaining useful life of every subcomponent, every supercomponent, and the machine and the network of machines. And based on the internal and external dynamics of the situation, to exactly predict when these components will fail. So obviously, if they fail in the planned maintenance periods, you're okay. It's very good. You don't have a problem. But if they fail between those, a sudden failure, what do you do? First of all, you need to know that it happens with high accuracy. And if it does, what sort of strategy you should take? Although, so for example, you change the component before this happens. So you basically take the component which is still has some good remaining useful life. What is the cost of that? What is the risk to that? Or you're allowed to break down in that period and know about what is the impact of it, what is the risk. Or you give an advice on how to extend the useful life. So change the setting of the machine until it reaches to the next system. And we have now achieved this. I was giving a speech in the global aviation industry for predictive maintenance of aircrafts. And when I said that this zero sudden breakdown, they have something called aircraft on the ground, AOG. They said if our aircraft is not functional, is not in the air, it's not $5 million an hour, it's tens of millions of dollars cost to us. Nowadays, many low-budget airlines, many systems that are under pressure to reduce costs, they are really worried of their preventive or predictive maintenance plans. So they do change a lot of good components of aircrafts way ahead of its real remaining useful life. So if we can come up with a much better and accurate predictive maintenance for them, is highly desirable. Although the industry is highly conservative, but we are hoping to make some breakthroughs there and provide some systems in that area. But this zero breakdown system is now a highly desirable system. I am now in negotiations with a number of large automotive industries, a lot of other industries and production systems who are very keen on implementing these sort of solutions. Our systems now highly accurately predicts when the system breaks down to near what we call determinism. So very accurate and high confidence. However, the interesting thing was that because I'm a very nosy person, and as a systems engineer, we want to poke our nose to the business of everybody in the world. Recently, in the last 5-6 years, I have tried to convince the process industry, especially the biological process of food industry, water industry, biorefineries, that our system will work within their environments as well. And to some success, we have now a number of projects that we are transferring or creating digital platforms for traditional, highly traditional systems like water and wastewater plants and refineries. In this process, we use the same techniques, but as you know, our processes are now much more volatile, less prone to understanding of capturing mathematical models. So they are very much black box solutions or gray box solutions. Even the physical models that we have, for example, fluid mechanics models, mass flow analysis, et cetera, they are just generic models, and they don't really work in a solid waste modeling, for example, and wastewater treatment plants, where you're dealing with bacteria and photosynthesis and the way they behave against the physical environment that they're in. So in this environment, we use the same mechanisms to improve and adjust or create new physical models or inferential models with similar key performance indicators. Again, translating these functions into operational information. So from engineering environment, physical system, digitalization, and operational management. Now, in these systems, because of our the requirement of objective function, instead of cost, circular economy functions are now being optimized. So we create a circularity index. This is all about recovering material from wastewater, urban waste, extracting minerals, extracting energy, water, preserving and reusing water. So our objective function is more to meet circular economy platforms. So we're going from engineering solutions to adding socio-economics constraints to the system. So the complexity of these systems are tenfold, I can say, exponentially increases in comparison with a well-defined environment of classical manufacturing. They have much more complexities into them and many more unknowns. We're now dealing with this. We have at least, I'm running around 12 projects in this area. So, going back to a recapture of what I've said until now. If you remember those circles in I think it was the 5th or 6th slide, the processes of data acquisition, data analytics, modeling, simulation, decision and implementation. All this revolves around a new paradigm. A paradigm of intelligence and digitalization. It was very interesting. Some time ago, I was given a talk in European ICT for water, or digital water, they called it. So you have very traditional chemical engineers and water engineers who are now getting familiarized and interested in this process of digitalization and smartification of systems. But they still are struggling to understand what's going on. So I suddenly thought somehow I need to tell them what this means. What were we doing? So I told them, okay, I'll give you an example. Human beings are considered the most intelligent and most sustainable, most aggressive creatures in the world. The reason that they have this capability is that they use 5 senses: seeing, hearing, smelling, touching, and so on and so forth. Some of us claim to have 6th sense. Its body is built incredibly well to collect this information. It has a phenomenal mechanism to translate the data that it acquires from the physical world. It translates it to voltage, to electrical pulses. That's how it translates what we see in the physical, or what we sense in the physical world. And through its neural system, which is a network of communication platforms analogous to our internet, it collects all this information and sends it to a center in our spine called the dorsal horn. The dorsal horn doesn't make decisions for it. What it does a very quick data analytics. So it manages the information, it classifies, it sort of filters, it improves, it creates packets. So it does a pre-processing, all through electronic means and electrical means, and sends this information to our brain. Our brain is a center of merging historical information that we call knowledge and experience. It mixes this real-time data with previous knowledge and creates an interpretation of the world. And that's how the physical world is translated to intelligence and electrical means and digital means. So next time, I hope, I don't know whether this analogy really works for you, but if anybody asks you what is the process of digitalization, maybe the best example is human being. So at the heart of this continuous infinite loop, we generate and build intelligence and interfere and intervene, improve our data acquisition capabilities, improve our data analytic capabilities, improve our simulation, our decision-making, and change of the physical system to retain and maintain sustainability and viability. On 24th of October, I visited I was invited to go to BMW to observe the production line plant in BMW, the mini factory in Oxford. You can imagine with COVID how important. I felt like I was the president or the prime minister of the UK, the way I was treated and given access. I can tell you that the company like BMW in the next 5 years is going to heavily invest on this transition to Industry 4.0. They are going to have smarter production lines. They're going to change all their existing machineries. Huge investment is going in. And hopefully I'm lucky to be part of that evolution. It's very interesting. They're saying that their current competitors is Mercedes and Tesla. But their new competitors, look at them. It's Amazon, it's Apple, it's Dyson, it's Google. These companies, these giants are known for what? They're not known for car making. They're known for their ability to create intelligence and deploy intelligence in optimizing and improving systems performance. In their earlier days, they specialized on their own speciality. But now, because they have embedded some of these technologies and improved and increased those capabilities to a phenomenal state, they are now able to do whatever they want. If they want to go into making cars, they'll probably make the most intelligent cars. You know, most of these institutions have invested heavily on autonomous vehicles. And they will soon be producing new transport systems that are highly, highly competitive with these. I will leave you with some of the sample publications from my research group. And I hope this talk, you enjoyed the talk and it gave you some limited insight to the interesting things that we do. And what really makes me get up early every morning and smile, because never in the history of mankind and its evolution towards industrialization, it has been good for systems engineers and control engineers. The time is the best time for people like us to make an impact and to reap the benefits of this mass exodus. We are the tools, and we are the pioneers, and we are the leaders of this. Equip yourself with the tools and techniques, and go out there and sell yourselves, because this is the time that all countries, all major economies in the world, from United States to Europe, to Russia, to China, to the emerging economies of the BRIC countries, they are all investing in smartification. Huge amount of money is going in. And they need experts. They need people who not only talk the talk, but also walk the walk. They have in their toolbox the instruments, the tools that can be deployed. Be very careful. If you claim something, go in with those equipment. If you cannot do it on your own, use your colleagues. Nowadays, there's nothing called one-man show. It's a multidisciplinarity that is successful. Create a combination of expertise and experience with the right equipment and go in and solve big problems. Thank you very much.
Thank you very much, Dr. Musavi. It was very inspirational, especially the last part, very interesting, very enlightening presentation. We have a couple of questions. First of all, you emphasize the point that socioeconomic factors, socioeconomic indicators will play much larger role in the modeling and so on and so on. But in my opinion, social economic factors depend largely on the values and beliefs of the person who is describing them. Does it mean that we are introducing, by analogy as quantum observer, quantum engineer, and we have to model for the person of engineer who makes the model?
A very good question. I think as a systems engineer, we have to go from singularity to mass. You're absolutely right. We have to start solving the problem of individualism, find the relationship between this individual with the next proximity and the next proximity. And slowly, the values, and find the commonalities of those values. Therefore, the design of the system that you're building all depends on the target and the focus that you have. If it's on singularity, then build your system around your singular. If it's growing, then you go around. So you're absolutely right. We have to look at the values. So, things become even more difficult, the values of people. Our projects, especially the ones that are in waste management and water industry, we are forced now to collect information from the people's views. Part of this project is to survey and extract information from the end user or the ones who are going to be part of this development. So we are asking farmers, for example. We are including the farmers. Because the only way you can tell a farmer that my solution as a systems engineer who has no history about farming, that if you put this solution in your farm, you better utilize the water, you increase the growth of your crop, he will say, go get lost. I have been doing this generations to generations. How dare you come with your computer and tell me that I know what to do and you don't? So the only way you can accept this, you have to go from that quantic view and shadow the needs. A sustainable system, an aggressive, sustainable system, not only adapts, but influences. So through that interaction with your social group, you not only they form your views, but you also influence their views as well. And then you find the commonality and you link the two sides. I don't know whether I answered the question.
Yeah, thank you very much. And second question, partially rephrasing the question from the chat. Is it too early to start talking about Industry 5.0? And do we know anything about that, or it's just distant future? Don't think about it; it will come on.
That's a very good point. You see, if you look at it, it's very interesting. When I was asked by EU Commission to write the new definition and new description of Industry 4.0, I was wondering, because the Industry 4.0 was basically a brainchild of the German industrialists and researchers. I was wondering why we have Industry 1, 2, 3, and suddenly 4.0. And I realized it's very much like versions of software. Mm-hmm. So people are now thinking, okay, we may not have a major sort of evolution that makes us shift to 5. We may go to 4.1, 4.2, 4.3. So I would assume that there is still another 20 or 15 years of us generating these tools and implementing the 4.0, because we're it's still the early stages. But what Industry 5 will imply, what I would think that seamless connectivity of all systems, mm-hmm. all the knowns, known knowns, and unknown knowns, and known unknowns. So basically, the totality, and then a quantic.
Yep.
So I would assume that would be the natural evolution.
Okay. Well, thank you once again for your wonderful presentation. We hope to continue our collaboration on next year conference. And once again, thank you very much.
It has been a great pleasure. Thank you very much.